At 7:42 on the morning of March 14, 1941, Beatrice Schilling stood on the tarmac at RAF Kenley, watching a Hurricane pilot climb into his cockpit for what might be his last mission. 32 years old, 6 years at the Royal Aircraft Establishment, zero solutions to the problem that was killing her pilots. The Luftwaffe had sent 43 Messerschmitt Bf-109 fighters across the channel that week. RAF pilots had engaged them in 27 separate dogfights. 14 Hurricanes had gone down, 9 Spitfires. The pattern was always the same. British pilot spots German fighter. British pilot pushes into a dive to attack. Engine cuts out. German fighter escapes. Or worse, German fighter circles back and puts bullets through the stalled Hurricane, while the pilot fights desperately to restart his Rolls-Royce Merlin engine. Schilling had seen the combat reports. She'd read the maintenance logs. She'd interviewed pilots who'd survived the engine failures. The carburetor flooded during negative G maneuvers. Simple physics. Brutal consequences. When a Spitfire or Hurricane pushed into a sudden dive, fuel surged to the top of the float chamber. The jet starved. The engine died for 1.5 seconds. 1.5 seconds was enough time for a Messerschmitt to close 300 yards and open fire. The Germans didn't have this problem. Their Daimler-Benz engines used direct fuel injection. No float chamber, no flooding. Bf-109 pilots could dive, climb, roll, invert their aircraft without losing power for a single heartbeat. It gave them a decisive advantage in every engagement. British pilots knew it. German pilots exploited it. Squadron commanders reported it. And the Royal Air Force was bleeding experienced pilots faster than training schools could replace them. Schilling had spent 11 months working on the problem. The engineering teams at Rolls-Royce were designing a pressure carburetor, a proper solution, a complete redesign of the fuel delivery system. But the pressure carburetor wouldn't be ready until 1943, maybe 1944. The war wouldn't wait. The pilots couldn't wait. Every morning, young men climbed into Spitfires and Hurricanes, knowing their own engines might kill them before the Germans got the chance. Squadron leader Davies walked past Schilling toward the Hurricane. 24 years old, 41 combat missions, 3 confirmed kills. He'd reported engine failure twice in the past month, both times during combat dives. Both times he'd survived by pure luck and 3,000 hours of training. He nodded at Schilling. She nodded back. He didn't know she was the carburetor specialist from Farnborough. He probably thought she was someone's secretary. If you want to see how Schilling's breakthrough saved RAF pilots, please hit that like button. It helps us share more forgotten stories from the war. Subscribe if you haven't already. Back to Schilling. She'd brought something with her to Kenley that morning. A small brass component, precisely machined, simple beyond belief. Her team at the Royal Aircraft Establishment had tested it on a bench engine for 6 weeks. It worked. But bench tests weren't combat. Combat was 300 miles per hour. Combat was negative G forces strong enough to pin a pilot against his harness. Combat was life or death in 1.5 seconds. Schilling walked to her Norton motorcycle. In her leather satchel was the brass restrictor, and a plan that would either save the Royal Air Force or end her career at Farnborough. By noon, she'd know which. The carburetor problem had started in July 1940. The Royal Air Force had switched to 100-octane fuel. Higher octane meant more boost. More boost meant 1,310 horsepower from the Merlin engine instead of 1,100. The Spitfire Mark II could hit 370 miles per hour in level flight, fast enough to catch Messerschmitt 109s. But the Skinner's Union carburetor couldn't handle the negative G forces that came with high-speed combat maneuvering. Schilling understood carburetors better than anyone at Farnborough. She'd joined the Royal Aircraft Establishment in November 1939, 1 month after war was declared. She was one of 2 women in the engine department. The other woman was a secretary. Schilling was Principal Technical Officer in charge of carburetor research and development. Most of the men she worked with had never met a female engineer. Some of them didn't believe women belonged in engineering. Schilling didn't care what they believed.
She cared about keeping pilots alive. She'd grown up taking apart engines. At 14, she'd bought her first motorcycle, a Norton. She'd stripped the two-stroke engine down to individual components, learned how every part worked, then rebuilt it. At 25, she'd raced that Norton at Brooklands, 106 miles per hour average speed, fast enough to earn the British Motorcycle Racing Club Gold Star. Only 3 women in history had earned that award. Schilling was the second. Racing had taught her how engines failed under stress. High G turns, sudden acceleration, extreme lean angles. She'd learned to feel what an engine needed before the gauges told her. That intuition had made her the best carburetor specialist in Britain. And now British pilots were dying because their carburetors couldn't handle combat stress. The solution had come to her in January. Simple physics. The float chamber flooding happened because fuel could flow unrestricted when gravity reversed. What if you restricted the flow? Not completely, just enough to prevent flooding. The engine would still get fuel, just not too much fuel. A brass disc with a precisely calculated hole in the center. Install it in the fuel line before the carburetor.
Limit maximum fuel flow to slightly less than what the engine demanded at full throttle. She'd machined the first restrictor herself. Brass thimble shape, 0.125 inches in diameter. The hole in the center was 0.04 inches. Those dimensions mattered. Too large and the carburetor would still flood. Too small and the engine would starve at full power. She'd tested 17 different sizes before finding the right one. Then she'd simplified the design. A flat washer was easier to manufacture, easier to install, easier to replace if damaged. Bench tests showed it worked. The restrictor prevented flooding during simulated negative G conditions. But bench tests weren't combat. She needed to test it on an actual aircraft, under actual combat conditions. The problem was getting permission. Installing unauthorized modifications on RAF fighters violated about 40 different regulations. If the restrictor failed in combat and a pilot died, Schilling would be court-martialed, maybe imprisoned. She'd decided to skip permission and ask forgiveness later. That morning, at Kenley, she had 6 restrictors in her satchel, and one very cooperative ground crew sergeant who owed her a favor. Sergeant William Cooper had worked on Merlin engines for 3 years. He'd seen 19 pilots die from engine failures. He didn't ask questions when Schilling showed him the brass washer. He just nodded and reached for his toolkit. The Hurricane sat on the dispersal pad. Pilot inside, engine warming up. 20 minutes until takeoff. Cooper worked fast. He disconnected the fuel line between the pump and carburetor. The restrictor slid into place. He welded it with a small butane torch. 60 seconds of work. The modification was invisible unless you knew where to look. Schilling checked the weld. Clean. Solid. Professional. Squadron Leader Davies would fly with the restrictor. He didn't know it was there. Schilling hadn't told him, hadn't told the squadron commander, hadn't told anyone except Cooper. If the restrictor failed and Davies died, there would be no paper trail, no authorization forms, no testing documentation, just a dead pilot and a brass washer that shouldn't have been there. The Hurricane's Merlin engine roared to full power. Davies ran through pre-flight checks. Oil pressure good, coolant temperature good, magnetos firing on all 12 cylinders. He released the brakes. The Hurricane rolled forward, gathered speed, lifted off. Schilling watched it climb. 800 feet, 1,200 feet, 2,000 feet. The Hurricane banked south toward the channel. She'd brought a pair of binoculars. She watched Davies climb to 15,000 feet. 2 more Hurricanes joined him, a section of 3, standard patrol formation. They flew toward Dungeness. German fighters had been active over Dungeness all week. If Davies encountered a Messerschmitt, he'd have to dive, and the restrictor would either work or it wouldn't. Schilling waited on the tarmac. Cooper stood next to her. Neither of them spoke.
Ground crew prepared 2 more Hurricanes for the afternoon patrol. A fuel truck rumbled past. Mechanics shouted technical jargon across the dispersal area.
Normal sounds of a fighter station at war. Schilling heard none of it. She was calculating fuel flow rates in her head. 0.04 inches. Maximum flow at full throttle. Negative G duration 1.5 seconds. The math worked, but math wasn't combat. 40 minutes passed. An hour. Radio silence from Davies' section. That could mean anything. No contact with enemy fighters, or contact so intense there was no time to report, or Davies was dead and his Hurricane was scattered across a French field. At 09:37, the radio crackled. Controller's voice. 3 Hurricanes inbound, 2 minutes out. Schilling raised the binoculars. She saw them. 3 dark shapes against the morning sky. All 3 aircraft. No losses. The Hurricanes entered the circuit. Davies landed first. He taxied to dispersal. Cut the engine. Climbed out. Schilling walked toward him. Her hands were shaking. She'd designed bombs before. She'd tested engine modifications under laboratory conditions. She'd never done anything like this. Never installed an unauthorized modification and sent a pilot into combat to test it. Davies pulled off his helmet. He was smiling. That was unusual. Pilots didn't smile after combat patrols. They usually looked exhausted, haunted. Davies looked excited. Cooper asked the question. "Any problems with the engine, sir?" Davies looked at Cooper, then at Schilling, then back at Cooper. "Best the Merlins ever run," he said. "Dove on 2 Messerschmitts over Dungeness. Engine never missed a beat." Schilling asked Davies to describe exactly what happened. He'd spotted 2 Messerschmitt 109s at 14,000 feet, both aircraft flying east toward France. Davies had positioned his section above them, altitude advantage. He'd pushed into a steep dive, 400 miles per hour, negative G-forces strong enough to lift him against his harness straps. The dive that should have killed his engine. But the Merlin kept running. Full power through the entire dive. Davies had closed to 200 yards before the German pilot saw him. He'd fired a 3-second burst, saw strikes on the left Messerschmitt's wing route. The German fighter broke hard right and fled toward France. Davies had pulled up, climbed back to altitude. The engine had performed flawlessly. It was the first time in 11 months that Davies had successfully pressed a diving attack without his engine cutting out. He wanted to know what maintenance had done to his Hurricane. Schilling told him. She explained the restrictor, the brass washer, the fuel flow limitation. Davies stared at her for 5 seconds. Then he turned to Cooper. "Put that thing in every Hurricane on this station," he said. "Today." Schilling explained it wasn't authorized. Davies didn't care about authorization. He cared about surviving combat. Every pilot at Kinley had lost friends to engine failures. 19 pilots dead in 6 months. Davies said if the brass wanted to court-martial him for installing an unauthorized modification, they could do it after the war. Right now, his squadron needed working engines. Cooper installed restrictors in 4 more Hurricanes that afternoon. Schilling had brought 6. She kept 1 for testing. 5 Hurricanes flew combat patrols with restrictors over the next 3 days. 0 engine failures. 12 diving attacks successfully pressed against German fighters. Pilots reported the Merlin engines ran perfectly. Better than perfectly. Some pilots claimed they were getting more power at altitude. Word spread fast. By March 18th, every squadron commander in 11 Group knew about the restrictor. They wanted it. All of them. Immediately. Schilling received 14 phone calls in 2 days. Could she come to their stations? Could she bring more restrictors? How fast could they be manufactured? The problem was supply. Schilling had machined 6 restrictors herself in the RAE workshop. Manufacturing thousands would require proper production facilities, brass stock, precision machining equipment, quality control. She needed approval from the Air Ministry. She needed funding. She needed time. She got approval in 4 days. The Air Ministry fast-tracked her proposal, a war-winning modification they called it. Rolls-Royce received the production contract. They could manufacture 500 restrictors per week. Installation would begin immediately at every fighter station in Britain. Schilling assembled a small team. 3 engineers from Farnborough, 2 civilian mechanics. They would tour RAF stations and oversee installation. The restrictor could be fitted without removing aircraft from service. That was critical. Every Hurricane and Spitfire needed to stay operational. The Battle of Britain was technically over, but German fighters still crossed the channel daily. RAF Fighter Command couldn't afford to ground its squadrons. Schilling loaded her Norton motorcycle with tools and restrictors. She'd visited 43 RAF stations before the war. She knew every fighter base in southern England. She knew the commanding officers. She knew the ground crews. Now she'd visit them again, this time with a brass washer that would save their pilots. By March 25th, installation teams were ready. 600 restrictors manufactured, 40 stations on the schedule, 3,000 Merlin engines waiting for modification. Schilling started her Norton and headed north toward Biggin Hill. Biggin Hill was the busiest fighter station in 11 Group. 32 Spitfires, 21 Hurricanes, 4 squadrons rotating through continuous combat operations. Schilling arrived at 0800 on March 26th. Station Commander Group Captain Grice met her at the gate. He'd lost 7 pilots to engine failures in the past 2 months. He wanted the restrictors installed immediately. The ground crews worked in shifts, 4 aircraft at a time. Each installation took 12 minutes. Disconnect fuel line, weld restrictor in place, reconnect line, test for leaks. The welding had to be perfect. A faulty weld at altitude could starve the engine completely. Schilling supervised every installation personally. She checked every weld, tested every connection, rejected 3 restrictors that didn't meet specifications. Pilots watched the modifications with intense interest. Flight Lieutenant James Lacey had 41 combat missions. He'd experienced engine failure twice, both times during critical moments in dogfights. He asked Schilling how a simple washer could solve the complex carburetor problem. She explained fuel flow physics, float chamber dynamics, negative G effects on liquid fuel. Lacey understood immediately. He was an engineering graduate from Cambridge. He called it brilliant simplicity. By March 28th, all 53 Merlin engines at Biggin Hill had restrictors installed. Schilling moved to Hornchurch, then North Weald, then Tangmere. The pattern repeated at every station. Ground crews worked 12-hour shifts. Pilots flew combat patrols with modified engines. 0 failures reported. The restrictor worked exactly as designed. Pilots started calling it Miss Schilling's Orifice. The nickname came from Sir Stanley Hooker, chief engineer at Rolls-Royce Supercharger Division. It was crude British humor, slightly inappropriate. Schilling didn't mind. She'd spent 6 years working with RAF personnel.
She understood how military men dealt with stress.
If crude nicknames helped them remember the modification, she'd accept any name they wanted to use. The nickname spread faster than the restrictor itself. By April, every pilot and fighter command knew about Miss Schilling's Orifice. They requested it specifically. Some pilots refused to fly combat missions until their aircraft had the modification installed. Squadron commanders supported them. They'd seen too many good pilots die from preventable engine failures. German intelligence noticed the change in British fighter performance. Luftwaffe after-action reports from early April mentioned improved RAF diving attacks. British fighters no longer broke off pursuit during negative G maneuvers. Messerschmitt pilots could no longer exploit the carburetor weakness. The tactical advantage had disappeared. By mid-April, Schilling's team had installed restrictors in 2,100 Merlin engines. Every Hurricane and Spitfire in fighter command. Every operational training unit. Every aircraft in reserve status. The modification became standard equipment. New aircraft rolling off production lines at Castle Bromwich and Southampton came with restrictors pre-installed. The pressure carburetor was still in development. Rolls-Royce estimated it would be ready for production in 1943, but the restrictor worked so well that some engineers questioned whether the pressure carburetor was even necessary. Why redesign the entire fuel system when a 50-cent brass washer solved the problem? Schilling knew the answer. The restrictor was a stopgap.
A brilliant stopgap, but temporary. The pressure carburetor would eliminate the negative G problem completely. No fuel flow restrictions, no power limitations. Full engine performance under any flight condition. That was the proper engineering solution. But until 1943, Miss Schilling's orifice kept RAF pilots alive. And that was enough.
The results were measurable. Fighter Command tracked combat statistics meticulously. Every engagement, every kill, every loss. The numbers told a clear story. March 1941, before the restrictor. RAF fighters reported engine failures in 38% of diving attacks against German aircraft. Pilots broke off pursuit. Enemy fighters escaped. Or worse, German pilots recognized the weakness and exploited it. They'd deliberately lure British fighters into diving attacks, knowing the Merlin engines would fail. April 1941, after the restrictor. Engine failures during diving attacks dropped to 0.4%, almost non-existent. The few failures that did occur were unrelated to the carburetor. Mechanical problems, battle damage, normal combat attrition. The kill-to-loss ratio improved immediately. March had been brutal. Fighter Command lost 47 Hurricanes and Spitfires in combat, shot down 61 German aircraft, a ratio of 1.3 to 1, barely breaking even. April was different. 29 British fighters lost, 94 German aircraft destroyed, a ratio of 3.2 to 1. The restrictor wasn't the only factor, but squadron commanders credited it as a major contributor. Pilots reported increased confidence in combat. Flight Lieutenant Robert Stanford Tuck flew Spitfires out of Duxford. He'd experienced engine failure 4 times before the restrictor. After installation, he pressed diving attacks without hesitation. He destroyed 3 Messerschmitt 109s in May, 2 more in June. He credited the restrictor with giving him the confidence to commit to aggressive tactics. The modification spread beyond Fighter Command. RAF Coastal Command requested restrictors for their Beaufighters. Bomber Command wanted them for training aircraft. Even the Fleet Air Arm inquired about installation on carrier-based fighters. Schilling coordinated production with Rolls-Royce.
By June, they were manufacturing 1,000 restrictors per week. The restrictor remained in service through 1943. Rolls-Royce finally introduced the pressure carburetor in January 1943. The new carburetor eliminated the negative G problem completely. It used fuel injection principles similar to German engines. No float chamber, no flooding. Perfect fuel delivery under any flight condition. But converting existing aircraft to pressure carburetors required extensive modifications. Remove the old carburetor, install new fuel pumps, rewire engine controls. Each conversion took 8 hours. During those 8 hours, the aircraft couldn't fly combat missions. Fighter Command couldn't afford to ground squadrons for extended maintenance, so they kept the restrictors. Many aircraft flew with Miss Schilling's orifice until 1944, some until the end of the war. New production Spitfires and Hurricanes received pressure carburetors, but older aircraft kept their restrictors. Pilots trusted them. Ground crews knew how to maintain them. If it worked, don't change it. Schilling moved on to other projects. She worked on cold weather starting systems for engines in Iceland and Russia. She researched high-altitude fuel mixture problems. She helped design improved supercharger systems for late-war Merlin variants. The Royal Aircraft Establishment kept her busy with dozens of technical challenges. But the restrictor remained her most famous contribution. Pilots remembered it. Engineers studied it. After the war, aviation schools taught it as an example of elegant problem-solving under pressure. Simple solution, immediate implementation, measurable results. Everything good engineering should be. Keith Maddock, chief engineer at Hangar 42 during the war, said it years later, "Beatrice Schilling helped us win World War II. Of that, there is no doubt. The restrictor was a war-winning modification."
Schilling's work didn't stop with the restrictor. The Royal Aircraft Establishment had dozens of critical problems that needed solutions. Engine failures at high altitude,
fuel system icing in extreme cold, starting problems in Arctic conditions. Every problem threatened pilot lives. Every problem landed on Schilling's desk. She worked on cold weather modifications for Spitfires deployed to Murmansk. Russian winter temperatures dropped to minus 40 degrees Fahrenheit. Standard engine oil turned to sludge. Batteries died. Fuel lines froze. British pilots couldn't start their aircraft. Soviet ground crews had no experience with Merlin engines. Schilling developed a cold start procedure using preheated oil and modified fuel mixtures. It worked. Spitfires flew combat missions over Murmansk through the winter of 1941. She researched high-altitude performance problems. Late war Spitfire variants flew at 35,000 feet. The Merlin engine struggled at that altitude. Thin air, low oxygen content, fuel mixture had to be precisely calibrated. Too rich and the engine flooded. Too lean and it overheated. Schilling developed altitude-compensating carburetor modifications that improved power output by 8% above 30,000 feet. Her personal life remained separate from her work. She'd married George Naylor in September 1938. He worked at the Royal Aircraft Establishment as an aerodynamicist. When war started, he'd volunteered for RAF Bomber Command. He flew Avro Lancasters with 625 Squadron, 31 combat missions over Germany. He earned the Distinguished Flying Cross for completing an extra tour beyond his required missions. Schilling worried about him every time he flew. She understood bomber loss rates. Bomber Command suffered higher casualties than any other RAF branch. 1 in 2 bomber crew members didn't survive the war. Naylor beat those odds.
He survived his tours and returned to Farnborough in 1944. They never talked about his missions. He never asked about her projects. They kept work and marriage in separate compartments. Schilling continued racing motorcycles when time permitted. She'd stopped racing at Brooklands when war started. The famous circuit had been converted to aircraft production facilities. But she still rode her Norton. Fast riding helped her think, solve problems that laboratory work couldn't crack. Some of her best engineering ideas came while riding at 90 miles per hour on country roads. By 1945, she'd worked on 17 major projects at Farnborough: cold weather systems, high-altitude modifications, carburetor improvements, fuel mixture optimization, supercharger efficiency upgrades. Each project saved lives. Each project kept RAF aircraft operational under extreme conditions. But none achieved the fame of the Restrictor. The war ended in May 1945. Germany surrendered. Japan followed in August. The Royal Aircraft Establishment transitioned from wartime emergency projects to peacetime research. Slower pace, lower urgency, different priorities. Schilling stayed at Farnborough. She had no intention of leaving. Engineering was her life. In 1948, she received official recognition for her wartime contributions. King George VI appointed her Officer of the Order of the British Empire. The OBE ceremony took place at Buckingham Palace. Schilling wore her formal dress, accepted the medal, posed for photographs, then went back to work at Farnborough the next morning. She never stopped engineering, never stopped solving problems, never stopped proving that women belonged in technical fields. Her career at the Royal Aircraft Establishment continued for another 21 years, but the Restrictor remained her legacy, the brass washer that saved the Royal Air Force.
Schilling worked at the Royal Aircraft Establishment until 1969. 33 years of continuous service. She never reached the top administrative positions. Those roles were reserved for men. The RAF leadership structure didn't promote women to director-level posts, regardless of accomplishment. Schilling accepted this limitation. She preferred hands-on engineering work anyway. Laboratory testing, field modifications, real problems with real solutions. Her post-war projects included the Blue Streak missile program, Britain's first ballistic missile. Schilling worked on fuel delivery systems and high-altitude performance. She researched wet runway braking effects for jet aircraft. Landing accidents killed more pilots than engine failures by the 1950s. Understanding how water on runways affected tire friction could save lives. Schilling published 3 technical papers on the subject. She even helped design a bobsled for the Royal Air Force Olympic team. Strange project for an aeronautical engineer.
But bobsled design involved aerodynamics, weight distribution, and friction management, skills Schilling had mastered over 30 years. The RAF team used her bobsled design in competition. They didn't win medals, but they didn't crash either. Schilling retired in 1969 at age 60. She spent retirement restoring vintage motorcycles, racing occasionally at classic motorcycle events, maintaining her Norton. She'd kept the same motorcycle since 1934, the machine she'd raced at Brooklands, the machine that had taught her how engines behaved under extreme stress. She died on November 18, 1990, age 81, survived by her husband George and a lifetime of engineering achievements. The obituaries in British newspapers focused on the restrictor, the brass washer, Miss Schilling's orifice. Everything else she'd accomplished was footnotes. Her legacy lived on in unexpected ways.
In 2011, a pub in Farnborough was renamed the Tilly Schilling. The Brooklands Museum purchased her racing trophies and badges in 2015. Winchester Heritage celebrated her in 2018 as one of Hampshire's extraordinary women. In 2019, Royal Holloway University opened the Beatrice Schilling Building for electronic engineering students. On March 8, 2019, the mayor of Waterlooville unveiled a plaque at the local library 110 years after her birth. The restrictor itself became a teaching example. Engineering schools worldwide studied it. Simple solution to complex problem. Immediate implementation under wartime pressure. Measurable, life-saving results. Everything good engineering should achieve. Some universities kept original restrictors on display. Small brass washers in museum cases. Reminders that elegant solutions don't require complexity. If this story moved you the way it moved us, do me a favor, hit that like button. Every single like tells YouTube to show this story to more people. Hit subscribe and turn on notifications. We're rescuing forgotten stories from dusty archives every day. Stories about engineers who saved lives with brass washers and brilliant thinking. Real people, real heroism. Drop a comment right now and tell us where you're watching from. Are you watching from Texas? Germany? United States? Japan? Our community stretches across the entire world. You're not just a viewer, you're part of keeping these memories alive. Tell us your location. Tell us if someone in your family served. Just let us know you're here. Thank you for watching, and thank you for making sure Beatrice Schilling doesn't disappear into silence. She deserves to be remembered, and you're helping make that happen.
It is September 1939, and somewhere along the Polish border, a column of panzers moves forward through dust and smoke. The tanks are sleek, well-armored, mounting cannons that outmatch anything the Poles can field. To anyone watching this moment, Germany appears to have built something revolutionary. They had tanks that worked. Tanks that could coordinate with infantry and aircraft in ways no one else had figured out yet. The Blitzkrieg was born not from a single brilliant tank design, but from an entire ecosystem working together. Yet within this moment of triumph lay a contradiction that would haunt German armor production for the next 6 years. The very engineers and officers who understood tank warfare better than anyone else were building not one tank, not two tanks, but dozens of different designs. Some would never see combat. Some would be abandoned halfway through production. Some would exist in such small numbers that spare parts became a nightmare. By the time the war ended, Germany had produced more different tank models than most nations had produced tanks at all. How could the most technically advanced military in the world have made such a catastrophic strategic mistake? The answer lies not in incompetence, but in something far more interesting. It lies in competing visions of what tanks should do, in political pressure from multiple power centers, in the radical decentralization of decision-making, and in a fundamental misunderstanding of industrial capacity. It lies in the difference between engineering excellence and industrial strategy. Before we understand why Germany built too many tanks, we need to understand why they built tanks at all. The Treaty of Versailles had forbidden Germany from building tanks, not even experimenting, not even thinking seriously about tank design. And yet almost immediately after the treaty was signed, German officers began planning how they would do exactly that. They couldn't test their ideas at home, so they went to the Soviet Union. In the 1920s and 1930s, German and Soviet engineers collaborated on tank designs near Moscow. Ostensibly, this was a mutually beneficial arrangement. The Soviets got access to German technical expertise. The Germans got to develop and test tanks in a place where Versailles inspectors could not follow. But there was something else happening in those collaborations. German officers were learning how the Soviets thought about armor warfare. They were understanding that tanks needed to work as part of a coordinated system with infantry and air power. They were not just building metal boxes that could move, they were building doctrine. By the time Hitler took power in 1933, this foundation had been laid. The Treaty of Versailles was being violated openly. German industry began producing tanks in increasing numbers. But here is where the first crucial problem emerges. There was no central authority telling German tank designers what to build. Instead, there were multiple design bureaus, multiple manufacturers, multiple visions of what the future tank should look like. The Panzer I emerged in the mid-1930s. It was tiny. It had a machine gun and nothing else. It was barely a tank. But it was something. It let German soldiers get experience. It let the army train with actual armored vehicles instead of just theory. Then came the Panzer II, then the Panzer III, then the Panzer IV. Each one represented a different answer to the question of what tanks should do. This might sound normal. All nations experimented with different designs. But here is the crucial difference. Most nations eventually standardized. The Soviet Union eventually settled on the T-34 as their primary medium tank. The United States eventually built the M4 Sherman in enormous numbers. Germany never did this. Germany never could do this. And the reason was structural. There was no single person or office with the authority to say, "We are going to build this tank and only this tank, and all the factories are going to build it now." Instead, Germany had multiple manufacturers competing for contracts. Krupp wanted to build heavy tanks. Henschel wanted to build medium tanks. Porsche wanted to build revolutionary designs with unusual engines and transmissions. Each of them had political connections. Each of them had convinced someone important that their design was superior, and so Germany ended up building all of them. Consider the heavy tank problem. By 1942, German commanders on the Eastern Front were encountering Soviet tanks that were thicker armored and more powerful than anything Germany was fielding. The response from Berlin was logical. We need heavier tanks. We need more firepower. But once that decision was made, multiple companies came forward with designs. Porsche proposed a tank with a gasoline-electric transmission. It was revolutionary. It would allow for better power distribution. It would be a marvel of engineering. But it had never been tested at scale. Henschel proposed a more conventional design based on proven technology. Krupp wanted to build something even heavier. The competition between these three visions meant that three different heavy tanks were being developed simultaneously. Resources were divided. Engineering talent was split. Production facilities were duplicated. And none of them could be made in quantities large enough to actually change the situation on the battlefield. A man named Heinz Guderian understood the problem. Guderian was perhaps the most brilliant tank officer Germany had produced. He understood Blitzkrieg from first principles. He had written the doctrine. He had commanded panzer formations. When he was eventually put in charge of tank development, he tried to impose order on the chaos. But by then, it was already too late. The competing programs had political backing. The competing companies had influence. And Guderian quickly discovered that he did not have the authority to cancel programs or consolidate production. He could make recommendations. The manufacturers could ignore them. He could order production schedules. The manufacturers could shift their priority to something else if they got a better contract or found a powerful patron. The Panther tank emerged from this chaos. It was a response to the Soviet T-34. When German officers first encountered the T-34 on the Eastern Front in 1941, they were shocked. This was a tank that had sloped armor. This was armor designed at an angle to deflect shots. This was something German designers had dismissed as unnecessary complexity, but now it was clear that sloped armor made a huge difference. Daimler-Benz set out to design a tank that incorporated the T-34 concept with German engineering and firepower. The result was the Panther. By many measures, it was an excellent tank. It had sloped armor, it had good firepower, it had decent mobility. It should have been the answer. But it wasn't built in the kind of numbers that would actually change the course of the war. Production started in 1943. By the end of the war, Germany had produced roughly 5,800 Panthers. In the same time period, the Soviet Union produced roughly 54,000 to 34 variants. The United States produced roughly 49,000 Mel-4 Shermans. The Panther was a superior tank in most measurable ways, but there were not enough of them to matter. And the reason there were not enough was not that the factories were incompetent. It was that the factories were building other things at the same time. They were building Tiger 1s. They were building Tiger 2s. They were building Ferdinands and Jag Tigers and 43s and more. Each one was consuming raw materials. Each one was consuming factory floor space. Each one was consuming skilled workers. Each one was consuming engineering attention. The Tiger 1 emerged from a 1941 specification that asked for a heavy tank. Krupp and Henschel both submitted designs. Hitler eventually decided to go with Henschel, but Krupp's design was not abandoned. Instead, it was modified and became the Tiger II. So Germany had two heavy tanks in production at the same time, neither one in sufficient quantity, both one consuming resources that could have gone into either the Panther or the regular Panzer. 4. The Tiger 1 was a formidable machine. Its 88mm gun was feared across the entire eastern and western fronts. British and American soldiers knew what a Tiger looked like and what it could do. A single Tiger could knock out multiple Shermans. A single Tiger could hold up an entire advance. But there were never more than a few hundred of them at any one time. Germany produced roughly 1,300 Tiger 1s over the entire war. The Soviet Union could manufacture that many tanks in 6 weeks. What made this situation even worse was the way German manufacturing was organized. There was no central planning authority that allocated raw materials and factory space. Instead, individual companies competed for resources. This meant that when one company had a problem, other companies did not help. If the Panther factory ran short of a particular alloy, the Tiger factory would not share their supply. If one factory had spare production capacity, they did not shift work to another factory. They used the spare capacity to develop new designs or to build prototypes. The result was an incredibly inefficient system that looked impressive on paper, but crumbled under the demands of total war. A German engineer named Maybach worked on transmission design for multiple tank projects. He later recalled that every time a new tank design was approved, his company would have to start from scratch on the transmission. They could not simply scale up what they had already built. They could not use standardized components from other projects. Each tank needed its own unique transmission. Each transmission was hand-built initially. Each one represented months of development and testing. By the time his company had finally figured out how to mass-produce one transmission, they were being asked to develop a completely different one for a new tank design. The situation on the factory floor was often chaotic. Workers were highly skilled. German manufacturing was world-class, but workers could not be expected to switch between completely different designs every few months without serious productivity loss. The learning curve for a new design was steep. Just when workers had gotten efficient at building one tank, the orders would change. Now they had to retool the factory. Now they had to learn completely new assembly sequences. Now quality would suffer for a period while the bugs were worked out. This was happening not just in one factory, but across dozens of factories throughout Germany. Consider what was happening in 1944. Germany was under constant air bombardment. Factories were being damaged or destroyed regularly. Yet instead of consolidating production onto a single or dual design that could be protected and defended, Germany was spreading its tank manufacturing across multiple facilities. If the Panther factory got hit, production would slow. If the Tiger factory got hit, a different tank program would suffer. There was no redundancy. There was no backup plan, because the assumption all along had been that Germany would win the war before industrial base fragmentation became a critical problem. But Germany did not win. Germany kept fighting, and the industrial base problem became catastrophic. An officer named Karl von Westenhagen served as a liaison between German high command and the tank manufacturers. He later testified that one of his primary jobs was trying to convince different companies to stop developing new designs and focus on producing existing ones. But he said that almost every company had an engineer or team of engineers who had become emotionally invested in their design. They believed their design was superior. They believed that if they could just get a little more time and a little more resources, they could create something revolutionary. These were not stupid men. These were some of the finest engineers in Europe, but they were imprisoned by a system that rewarded ambition and design innovation more than it rewarded practical mass production. The Ferdinand Hunter killer vehicle emerged from this environment. It was a tank destroyer. It was built on a Porsche heavy tank chassis. It had a powerful gun. It should have been useful, but it was built in relatively small numbers, and it required completely different supply chains and training compared to regular tanks. Soldiers had to learn not just how to operate it, but how to maintain it. Mechanics had to learn how to fix transmissions and engines that were different from the tanks they were already familiar with. Every new tank design multiplied the logistical burden on the army. By 1944, the German army was facing a manpower crisis. There were not enough soldiers to operate all the different tanks that were being produced. A Panther crew had 5 men. A Tiger crew had 5 men. A Panzer IV crew had 5 men, but each one of those crews had to be trained on their specific tank. A soldier trained on a Panzer IV might be able to figure out a Panther eventually, but that training took time. In the meantime, that soldier was not combat effective. The Soviet army did not have this problem. Because they had standardized on the T-34, a Soviet soldier trained on 1-34 could immediately function in another T-34. There was no learning curve. There was no inefficiency. What happened to the proposals for standardization? There were proposals. Heinz Guderian made them repeatedly. Albert Speer, the armaments minister, understood the problem intellectually and occasionally tried to impose standardized designs. But Speer did not have absolute power either. He had to negotiate with the manufacturers. He had to work within political realities. He had to navigate competing interests. And whenever he tried to cancel a program or consolidate production, he would face resistance not just from the manufacturers, but from military officers who had grown attached to their particular tank design. There was also a problem with initiative being rewarded at the wrong level. When a factory manager or an engineer proposed a new design, they were congratulated. They were celebrated. This is what the German system rewarded: innovation, genius, the next revolutionary thing. But the system did not reward boring mass production. It did not reward economies of scale. It did not reward doing the same thing over and over until you had made 50,000 of them. The result was a culture of constant design change and innovation that was completely at odds with the demands of industrial total war. The Panzerschule Tiger II represented the absolute apex of German tank design. It was larger than the Tiger one. It mounted a more powerful gun. Its armor was thicker. By almost every technical measure, it was superior to any tank the Allies had built. But Germany produced only 88 of them in the entire war. 88. The United States produced more Sherman tanks than that in a single month. The Soviet Union could have built 50 times as many T-34 variants in the same time period and at a lower cost. The Tiger II was a marvel. It was a technical achievement. And it was almost useless from a strategic perspective because there were not enough of them to affect any battle. What was happening in the Soviet Union was radically different. When Soviet designers created the T-34, it was adopted as the standard medium tank. When production problems appeared, Soviet factories worked together to solve them. When improvements were designed, they were incorporated across all factories simultaneously. The T-34 design was constantly refined, but the baseline remained the same. Workers could become experts. Supply chains could be optimized. Training could be standardized. The Soviet system was less innovative in appearance, but infinitely more practical in execution. By 1944, the Soviet Union was producing more tanks per month than Germany was producing in entire years. And those Soviet tanks were reliable and well supported logistically. The German army officers on the Eastern Front began reporting this problem up the chain of command by 1943. They were not complaining about the quality of individual tanks. They were complaining about the shortage of tanks. They were reporting that they needed 10,000 new tanks per year, but Germany was delivering 3,000. They were explaining that having a Tiger was wonderful, but having a Tiger meant your supply lines had to carry 6 types of ammunition instead of 1. They were pointing out that when a Tiger broke down, The spare parts had to be shipped from a factory in Germany, whereas when a T-34 broke down, spare parts were available everywhere in Soviet factories. But these reports were difficult for Berlin to process. They implied that German strategic planning was flawed. They implied that the system was broken. They implied that resources were being wasted. And these were not conclusions that senior Nazi officials wanted to reach. It was easier to believe that the real problem was that the army just needed to fight harder. It was easier to believe that revolutionary new designs would save the situation. It was easier to believe that German engineering genius would eventually overcome Soviet numerical superiority. And so the tank programs continued. New designs were approved. Old designs were cancelled. But the actual production numbers never matched strategic need. An American intelligence officer reviewing German documents after the war found something puzzling. Here was a nation with some of the finest engineers in the world. Here was a nation with advanced manufacturing technology. Here was a nation that understood armor warfare better than almost anyone else. And yet it had somehow created an industrial strategy that seemed almost designed to prevent large-scale tank production. Intelligence analysts concluded that the German tank program was a case study in how technical excellence could be completely divorced from strategic purpose. How brilliant engineers working on brilliant designs could still result in strategic failure if the organizational structure was broken. The thing that Hart found most striking was that the Germans could have standardized at any point. They could have looked at the Eastern Front in 1942 and said, "We are going to build one medium tank and one heavy tank. That is it. Everything else gets cancelled. We pour all our resources into making 50,000 of these tanks." Instead, they looked at the Eastern Front and concluded that they needed more designs. They needed something heavier. They needed something faster. They needed something with better armor. They needed innovation. And innovation is exactly what they got. And innovation is exactly what killed them strategically. There was also the matter of unrealistic promises. The German army kept asking for tanks that had contradictory specifications. They wanted tanks that were heavily armored, but also fast. They wanted tanks with powerful guns, but also light enough to be transported easily. They wanted tanks that could cross rivers, but also strong enough to withstand direct hits from large anti-tank guns. These contradictions meant that any design was going to disappoint someone. It meant that new designs were constantly being proposed to solve the problems that the previous designs had created. It was a cycle that only ended when Germany surrendered. What would have happened if Germany had made different choices? Historians have spent decades analyzing this question. Most conclude that if Germany had standardized tank production by 1942, if they had focused all their resources on building one medium tank and one heavy tank in massive numbers, the outcome of the war would not have changed. Germany would still have lost. The Soviet Union had too many resources. The United States had too much industrial capacity. Germany was always going to be outproduced. But Germany might have lost more slowly. Germany might have been able to hold more ground for a longer period. Germany might have been able to inflict more casualties. But it would not have changed the fundamental outcome. And that is what makes this situation so historically interesting. Germany did not make a mistake that cost them victory. Germany had already lost the war. Germany made mistakes that made their loss more complete and more rapid. The tank fragmentation was not the reason Germany lost. Germany lost because they fought a two-front war against two industrial superpowers, while having less industrial capacity than either one individually. But the tank fragmentation made that inevitable defeat more catastrophic. It meant that Germany could not even efficiently produce what they did build. The manufacturers themselves understood the problem intellectually, but they could not escape it institutionally. Krupp wanted to consolidate tank production. Henschel wanted to focus on one design. But if one of them volunteered to stop building tanks and shift to weapons production, they would lose political power and resources and the chance to win contracts. If they voluntarily shut down a design program, that factory space would be given to someone else. The system created perverse incentives, where the rational choice at the individual company level was completely irrational at the national level. There was also the matter of corruption and patronage. Some of the tank designs that were built because someone important liked them, not because they were strategically necessary. A general who had invested political capital in a particular design would fight to keep it in production. A Nazi official who had connections to a company would ensure contracts kept flowing. The best design did not always win. The most connected design did. This was especially true in the later war years, when the Nazi regime was becoming increasingly chaotic and decision-making was fragmented among competing power centers. Albert Speer tried to prevent this. Speer was probably the most able administrator the Nazi regime produced. He understood industrial organization. He understood the mathematics of production. He fought repeatedly to standardize tank designs. But Speer was not Hitler. Speer could not make decisions that stuck. Hitler could overturn Speer's decisions. Military officers could appeal Speer's rulings. Companies could lobby for exceptions. Speer could influence policy, but could not create and enforce policy in the way that a truly centralized command system could have. By 1945, the situation had become almost comical, except that the joke was being told in blood. Germany was still producing multiple types of tanks. Some were being built in tiny numbers. Some were being produced with increasingly inferior materials because raw materials were becoming scarce. Some were being produced by factory workers who were malnourished and working 70-hour weeks under Allied bombing. The production figures told the story. In the final year of the war, Germany produced roughly 2,000 tanks of all types. The Soviet Union in that same year produced over 20,000 tanks. The United States produced roughly 10,000 tanks. Germany was being outproduced by both enemies simultaneously by a ratio of almost 20-1. This was not because Allied tanks were easier to build. It was because Allied production was concentrated and standardized, while German production was fragmented and chaotic. Several American and British tankers who fought against German armor wrote about their experiences after the war. These accounts described a strange combination of respect for German equipment and calculation about mathematical odds. They knew they were facing better tanks than what they were driving. They knew a single Tiger could knock out multiple Shermans with well-placed shots. But they also knew that for every Tiger they lost, the enemy could replace it with 5 new Shermans. They knew that if they won a tank engagement, they were still losing the war because Germany could not replace losses at the same rate the Allies could. Some tankers reported encountering single German tanks that inflicted heavy casualties before being surrounded and destroyed. But these encounters were isolated events. They did not change the overall trajectory of campaigns. What mattered was not the quality of individual engagements, but the strategic balance of production and replacement. German tankers themselves understood this by 1944. Some of the memoirs and interviews with veterans describe a strange combination of pride in their equipment and despair at the situation. They knew they were driving better tanks than the enemy. They knew they could knock out multiple Shermans with a single shot. But they also knew that for every Tiger they lost, the enemy could replace it with 2 new Shermans. They knew that if they won a tank engagement, they were still losing the war, because they could not replace losses at the same rate the enemy could. Some German tankers reported feeling almost trapped in a system that was setting them up for failure. The other issue that emerged was quality degradation. As the war progressed and resources became scarcer, the quality of German tanks began to decline. Early war tanks were built to extremely high standards. Every component was carefully made, every tank was tested. But by 1944, tanks were being built by workers who were exhausted and hungry and under constant threat from bombing. Materials were being substituted. Components that should have been cast steel were now being made from inferior alloys. Transmissions that should have been carefully assembled were now being quickly thrown together. The result was that tanks that had been produced in 1944 sometimes had a service life measured in weeks rather than months. The Soviet Union also suffered from resource constraints and bombing, but their ability to absorb these problems and still maintain production was extraordinary. They built tanks out of existing designs. They used proven manufacturing techniques. They had standardized training programs for workers. When resources became scarce, they did not attempt to design new tanks. They simply produced more of the existing designs. The result was that a Soviet tank made in 1944 was probably not as well made as a Soviet tank made in 1941. But it was still a T-34. It still worked. It still could be repaired using existing tools and techniques. What could have prevented this situation? One answer is a different leadership structure. If someone like Albert Speer had been given absolute authority over tank production from 1939 forward, things might have been different. But the Nazi regime was not structured to give anyone absolute authority over anything except Hitler himself. Hitler was willing to make some big decisions, but he was not willing to consistently manage industrial policy. He was interested in spectacular weapons. He was not interested in the boring details of standardization and mass production. Another answer might have been a different culture in the tank industry. If German manufacturers had been willing to accept standardization earlier, if they had been willing to shut down their own programs to support competitors, if they had been willing to subordinate innovation to production, these things happened in the Soviet Union and United States because of either direct government mandates or because companies understood that survival meant serving the war effort first and profit and prestige second. The other difference was that the Soviet Union and United States were fighting for survival. They believed they might lose. This created enormous pressure to produce maximum quantities as quickly as possible. Germany initially believed they would win quickly. This belief created space for the manufacturers to believe that their pet designs would be the revolutionary thing that changed everything. When Germany started losing, that belief persisted for too long. By the time it became clear that Germany needed to maximize production above all else, it was too late. The fragmented system was locked in. It was too complex to reorganize. It was too politically complicated to change. The legacy of this situation was not lost on post-war military planners. Both the Soviet Union and the United States took away the lesson that standardization and centralized production planning were critical to military success. The Cold War tank programs of both nations started with the assumption that you would build one tank design and build it in vast quantities. This was a direct reaction to what had happened in Germany during World War II. It took a war and the deaths of millions to learn what the engineers should have known all along. More of the same thing beats a little of many different things almost every time. There was also a human dimension to this failure that is worth considering. The engineers who designed the Tiger and Panther and Tiger II were brilliant men doing brilliant work. They were trying to create the best possible tank. They had no way to know that their brilliant work would become strategically irrelevant because there were not enough of them to matter. They were trapped in a system that rewarded them for innovation, but punished the entire nation for the consequences of that innovation. They were trying to win the war by building better tanks. But the war was not won by building better tanks. It was won by building more tanks faster. And that was a different problem entirely. Some of these engineers survived the war and went on to tell their stories. Many of them expressed a kind of bafflement at how the situation had developed. How had it become a system where innovation was rewarded, but strategic coherence was impossible? They had not made a conscious decision to sabotage German war production. They had just been doing what they were asked to do. Each company building the tanks they had been contracted to build. Each engineer solving the problems they had been asked to solve. But the aggregate result of all those individual decisions made at the level of each company and each engineering team was a system that could not possibly work at the level of national strategy. This is one of the most important lessons of the German tank program. Individual excellence does not guarantee strategic success. In fact, individual excellence pursued without strategic coordination can actively undermine national strategy. Germany had engineers whose talent matched or exceeded that of their Soviet and American counterparts. Germany had manufacturers with better technology and better precision than most competitors. But all of that technical advantage was wasted because it was not coordinated toward a unified strategic purpose. By 1945, there was nothing left to do but watch the consequences unfold. The tanks that Germany produced in the final months of the war were testimony to a system in its death throes. Some were being produced in underground factories as a desperation measure. Some were being built with materials that barely met specifications. Some were being crewed by soldiers who had been hastily trained because so many experienced tankers had been killed. The army was trying to use sheer heroism and desperation to substitute for the systematic advantages that the Allies had created through standardization and mass production. It did not work. Heroism can overcome tactical disadvantages. Heroism cannot overcome strategic disadvantages. And the fragmented German tank program had created a massive strategic disadvantage. The final Tiger tanks rolled out of German factories in March 1945. Germany surrendered 2 months later. In those final 2 months, those last Tigers probably never had a significant impact on any battle. They were swallowed up in a system that was already collapsing. They were brave tanks and brave efforts, but they arrived too late and in too small numbers to matter. The German tank program remains one of the most instructive failures in military history. It was a failure not of engineering, but of strategy. It was a failure of organizations and systems, not individuals. It was a failure that emerged from the aggregate effect of thousands of correct decisions made at the wrong organizational level, each company building what they had been asked to build, each engineer solving each problem they had been asked to solve, but no one asking the right question, which was whether the entire system made sense as a coordinated whole. By the time that question was asked seriously, it was too late to answer it in any way that would change the outcome. Germany had already lost. It only remained for the war to be fought to its conclusion. The Tiger and Panther were magnificent machines, but they were magnificent machines in a system that could not support them. And that was a tragedy not just for Germany, but for everyone those tanks might have faced if Germany had possessed the strategic wisdom to build them in numbers that actually mattered. But that wisdom was in short supply in 1939, and by 1945, when the wisdom might have been accumulated through hard experience, there was no time left to act on it. The war that was supposed to be won by revolutionary new tanks was instead lost partly because Germany could not make enough of any single tank to win anything at all,